But just because a lot of money has gone into that sort of way of thinking, a lot of people believe it's real, it's not. Okay, so what is real? Let's talk about how do we build systems and what kind of challenges do we have. All right, so first of all, if we're going to use this word intelligence, I was a neuroscientist for a while, a cognitive scientist, and I learned to appreciate the complexity of this thing up here, the brain. And so one way to think about it is that you're up on Mars, and you're a Martian computer scientist. And your computers are very primitive, and so you'd like them to be smarter, whatever that means, in the Martian sense of being smart. So you look down at Earth, trying to find inspiration for what intelligence could be. Okay, so what is there from the long distance away? What is there that's intelligent on Earth? Right. Well, somehow this is maybe the first thing you look at. You see these things. They seem to be doing something surprisingly intelligent. And you look down at a brain, and you see that it's composed of all these neurons. And then you realize a neuron is amazingly complicated. A neuron's a cell, and it's three-dimensional. It has these arborizations, and it has ions flowing over everywhere. These little synapses that are themselves whole like cities of chemistry and physics and electromagnetism and so on that. And they're storing memories in some way that the humans haven't figured out yet, and so on. That's just one neuron, and there's billions of these connected in this spaghetti-like web. Right, so as you may know, there's there's worms where there's maybe a few dozen or a few hundreds of neurons, and it's kind of mapped out, but we have no idea how those neurons lead to the behavior of the worm. Okay, so it is not going to be this decade, it's not going to be this century, it's going to be hundreds of years before we start to pick apart. This is the most complex scientific problem ever investigated, and we don't have the beginnings of the principles. So we're like the Greeks trying to think about sending rockets to the moon. Someday we know it'll happen, but it's not in our world. Okay. Similarly, even in understanding the intelligence of a child and how they reason about the world, how they get concepts so quickly, how they abstract, how they plan ahead, in spite of all the uncertainty around them and so on. We don't know, okay? So I've been watching this field for 40 years, and we still don't have a clue with these kind of things. What we do have is learning systems that can take in massive amounts of data and copy the intelligence that's in the data that comes from humans, or learning systems that can take branches down tree and explore billions and billions of possible moves and maybe find some that work, okay? So that's brute force search. And the other kind is kind of copy. So we don't have intelligence. Does that mean we have nothing? Well, of course, that's not true. We have brand new industries and brand new things that can happen. We've just got to be realistic about what we're talking about. All right, so now the Martians realize this. They're not stupid. They're looking down and they see, okay, we're not going to figure out the brain and the mind, all right? But is there something else on Earth that's intelligent, that's surprising it? Maybe we could build into our computers. So what else is there intelligent on Earth? Yeah, in some sense, ecosystems. That's the right way to think. You don't want to look at these little individuals and say, we got to copy one of them, right? You want to look at the overall system. So if you're ever taking an econ class, on day one, they say something like the following. Think about the city of San Francisco, and think about the food that it has coming into the city every day. Every restaurant has certain dishes it has, and they all need the ingredients for those dishes. And it just works. Trucks arrive, and buses arrive, and planes arrive, and the food that the city needs arrives day in and day out. Rain or shine, fire hazards or not. It works at all scales, villages, cities. It's been working for thousands of years. It being kind of microeconomic principles that make systems work out of disconnected parts, that each one do something minimally intelligent, make a decision whether to take their goods from one place of the city to another and sell them in some way. Right? We know something of the principles of that. That is the principle of microeconomics: supply, demand, mechanism, design, and so on. Right? And tragically, we're not using those principles in the design of our modern AI systems. We put out systems that make decisions, and they are unfair. They're biased. They don't do the right thing. Well, partly we're not thinking about the underlying economic principles that make fairness and bias part of the utility maximization problem. Okay? So I would argue that more than brains and minds, what we have already on Earth are markets that are by any definition that we can try to mimic in our lifetime intelligent. They are robust. They are adaptive. They work at multiple scales. They don't need software uploads. They do transfer learning. They can go for days and weeks and months. Now, of course, they're not perfect. They have all kinds of problems, but that's interesting. That makes them research challenges. If we try to put them in the computer, we're going to have to fix some things. We have to be engineers and think about it, not just assume they work. So there's wonderful, interesting challenges there. All right, so minimally what we know about brains and minds, which I think is minimal, put that together, Marcus, I think we start to have the glimmer of the beginning of an engineering field. Okay, so these are decentralized algorithms. They accomplish complex tasks. They're adaptive. they're scalable, they can work for long lifetimes. Doesn't it sound like intelligent systems to you? Okay? Okay, so what are we going to work on if we're going to take this kind of agenda? Well, there's lots of problems. The economists didn't solve many of the problems that had to do with data and computing and algorithms. And they were all about kind of just general equilibrium principles and so on. So, you know, multi-way markets where the individual agents need to explore to learn their preferences. In economics, you assume that you know the preferences of everybody, and then they play a game to kind of work it out. Right? But what if no one knows their preferences because they haven't had an experience yet? They don't know what they like. They don't know which restaurant's best. Okay? They have to try. Put that into economics. Who knows how to do that? That's interesting. Large-scale multi-way markets where each side of the market views the other side through a recommendation system. Recommendation systems had more impact than all the deep learning stuff we see right now. Okay? And then vision and speech and all that. Recommendation systems billion-dollar industries. Okay? It's simple in some level, not AI, but really important. Right? Well, imagine you're trying to build two-way markets between, say, diners and people and restaurant owners. But you're in China and you've got 500 million people and you've got hundreds of millions of restaurants. How do you do a matching of two sides of that market? It's hopeless at that scale. But if both sides have a recommendation system that reduces them to a small number of things that they like based on their past history, you can start to imagine a market that would clear at the right scale. Okay? How about that? How about information asymmetries in markets? People in economics don't know how to talk about that. We do. That's what inference is about. Latent variables, data collection, strategic settings. I'm trying to be strategic. What data should I collect to be better strategic? And how do I share information? How do I do free riding, watching somebody else gather information? How do I use that for me? All right, so how do we find principles like this and build systems that will work over long stretches of time? Okay, so let me say this one more time. This is slides I think I've used before, maybe even in this conference. This is my history of machine learning. So my history of machine learning is not that we had AlphaGo and then before that we had this, neural nets and all that. Those are show-off tricks, right? Here's what really happened. What really happened is that companies like Amazon built vast computer farms and brought in vast amounts of data to do things like fraud detection. You can't have online commerce without fraud detection not being at 3% like credit cards, but all the way down at 0.01%. So they got all the data they needed to get that fraud detection rate down, and they still work on that. Most companies do to this day. It's hard. It's a real machine learning challenge. Even more important, supply chain management. You're trying to serve billions of products to hundreds of millions of people and do it in 3 days. Those products have got to be ready at the right time in the right place and so on. So you've got to model all the ingredients in the supply chain, which is amazingly complex and rich thing to do. Hundreds of researchers were needed at Amazon in the 1990s to do this. They were all machine learning researchers, really. Okay? Right? No one talked about that. No one made big promises about AI and how we're going to solve all the world's problems, but they just went out and were good engineers. Having done that, they realized a lot of the data was not just about ships crossing the Indian Ocean and strikes in France. It was data about human beings, about what they were buying and what they liked and so on. So they said, well, can we provide new services? And that was the era of recommendation systems. Recommendations was another billion-dollar industry. Okay? And it was just data analysis. Take in some data about one person, transfer that to another person, do that at scale, and make it economically interesting and viable. I think the era we're in right now, the hype era, is about pattern recognition. So this is the phrase that Dugard Hart used. It's about gradient descent on bags of parameters based on labeled data, or it's about search algorithms. Okay? Fine, nothing wrong with those algorithms. They're just limited, and we shouldn't be talking about how far they're supposedly going to go. Moreover, there's not a billion-dollar industry yet. So yes, there are applications of computer vision and so on, but it's still, I don't see the billion-dollar industry. What I do see is an emerging fourth generation, which is flows of data, markets. It's not just one agent making decisions and we replace the agent with a computer, but huge new kinds of markets. So here's an example, the music market. There is no music market right now, okay? A few people make songs that they make millions of dollars off of, but it's like a tiny fraction of people. It's not even a monopoly. It's not even close to an economic model. On the other hand, if you look at the data, all the songs being listened to right this moment, mostly in inner cities, is music made in the last 2 years, and it's music made by people that are not famous. Because they're good, a lot of people make good music, they put it on SoundCloud, it gets streamed from Spotify, it's all our usual ecosystem, but there's no economic value flowing along any of those pipes. The person who makes the music has no idea that someone is listening to it, and they make no money off of it. And people talk about, a little subscription model, they'll get a little piece of it. That's not an economy. You can make an economy for musicians. It's not that hard. It's a good data science. You can start a company that does it. How do you do it? Right? Well, you go look at the data that's being streamed. For each person who's making the music, you show them a dashboard of At the end of the week, here is a map of the United States, and here's a place where one of your songs was listened to. And maybe you see that in Dayton, Ohio, 10,000 people listened to this person's songs last week. That person then can go show the venue owners in Dayton that they're popular in their city. The venue owners will let them give a show, they can make $20,000. Right? Moreover, they're connected now to the people who came to their show. It's a producer-consumer relationship. They can make offers. I'll come play your wedding for $10,000. You want to buy some merchandise, et cetera, et cetera. That's how you create an economy, type create jobs. And I can easily imagine 1 million people in this country having that kind of a musician job, a new kind of musician job. And a company will supply this. It's not the government, it's not just some hacker, it's a company that has to supply that platform. Right? And that company can make 5% of all the transactions and be a perfectly valuable company. It doesn't have to do any advertising to make its money. Okay? So see how easy this is if you think out of the box a little bit, if you think more like an economist about how do I create an economy. Okay? Now that's 1 million people who could have jobs in the United States. What about Brazil? What about China? What about Europe? All right? That's what needs to be starting to happen more. Instead of replacing jobs, let's aid jobs. Let's make more jobs by aiding humans. All right. So another way to say what's this emerging, I'm getting a little more technical now, what's this emerging set of challenges? Well, they have to do with decisions. So the neural net era is all about pattern recognition. So label data or search algorithms. Well, real life machine learning has to do with making decisions, not just finding patterns and showing, here's some task I can do. All right? So let's think about a decision with consequences, like a medical decision. So you go into your doctor's office next week, the doctor measures all kinds of things about your body, moreover, takes your genome, and so on and so forth. There's a 40,000 dimensional feature vector that goes into some big neural net that's been trained on some huge amount of data, and out pops some predictions, some treatment options for you. So if some number is over 0.7, that's a threshold, and the neural net is telling you better have a heart operation. All right? Is that a decision in any sense of the term? Well, no, not at all. Okay, you're not going to say, oh, I see, the neural net had the better data than me. It knows I'm going to have a heart operation. No, you're going to have a dialogue at that point. You're going to say, what data was that based on? What's the provenance of that data? Is it 10 years old? Is it 5 years old? Is it about people like me? Was it on the same machine I was on? You're going to want to do some what-if experiments. What if I were to change this thing about my diet? Do you know this thing about my family? Et cetera, et cetera. Can I get a second opinion? Real decisions involve all that kind of reasoning around a pattern recognition system, right? And our current systems aren't doing any of that reasoning, okay, except in very limited ad hoc situations. Our big AGI, so-called systems, are not doing any of it. They're not doing any semantic understanding, and they're not doing any reasoning around decisions. So it's not even remotely close to what we need. So real-world decisions with consequences have to have kind of be able to do what-if experiments, look at other data you might have gathered, talk about the provenance of the data, all the kind of things that good engineers do. We don't talk about. Now, it's not just one decision, however, of you sitting in the doctor's office. What it really is a large number of linked decisions. All of us are going to go to the doctor in the next month or year, and whatever treatment options come out, something that works for you should be available for the rest of us immediately. Right? The whole thing should be a federated, networked system. How do we build such a system? How do we worry about the privacy issues? How do we aggregate correctly? How do we worry about the provenance of the data? How do we keep it not stale? How do we build that big pipeline that creates such a system? Right? So people do talk about this. It's not that hard to talk about, but people make it really real and build, not very many. Now, it's not just about network decisions. It's about network decisions over time, and even more importantly, it's about decisions when there's scarcity and competition, when everyone can't have just what they want because they make a decision. All right, so here's where this started to become clear to me. I started thinking about recommendation systems, and I was thinking about this in context going to China, where a lot of people are building companies around a recommendation system. So here's a recommendation system for stock purchases. Here's one for restaurants. Here's one for paths to the airport, and so on. They were just downloading standard neural net software or pattern recognition software to do this, right? And those recommendation systems were doing things like making the same recommendation to large numbers of people, okay? Because that's what recommendation systems do, okay? Amazon system will recommend the same book or movie to huge numbers of people, no problem. But if you recommend the same street to huge numbers of people, you create congestion. If you recommend the same restaurant to huge numbers of people, that's a problem too. Right? How do you fix that? Do you get better data? Do you try to know more about the people so that you look at their browsing history and understand them better so that you know what restaurant they really should go to? No. You build an economy. You have a two-way market. Restaurants on one side, people on the other side. You try to connect them up, and bids go across. I arrive in Shanghai, pull up my cell phone. I don't know anything about the city. I can't speak the language. I want to hit a button, have it know things that geolocate me, know that I like Szechuan cuisine, know I have a certain price point, and broadcast that to all the restaurants around me. Okay? This is not that mysterious. This is like an Uber model or something, but done right. A real two-way market at scale where people participate and they have a lot of transparency in what's happening there. Okay? And critically, there's recommendation system use. I don't want to be connected to any possible restaurant in China. I want the restaurants near me, and I want the ones that are food I'm going to like, and I'm going to have a good experience. And that has to do with me as a person. So I need recommendations. Similarly, the restaurants need recommendations to look at the client side, because there's 500 million possible clients. They don't want every one of them. Right? They want to have some preferences based on their own history. Okay, so you can't recommend the same thing to everybody. My favorite example of this was stock price or stock purchase recommendation. So, you know, for the first time, people in China started to have some personal wealth. You know, a grandmother will have $1,000 or 100,000 RMB. So she said, I'd like to invest this. I'd like to make money off this. Right? So she doesn't know what to do, how to do that. She's never done that before. So she goes to her son and says, well, there's an app. You just download it on your cell phone, and the app will help invest for you. All right? So fine, but if you think about that, okay, if a very few number of people are using that, no problem. But what if everyone in China starts to use that app? It really becomes super popular, right? Well, that app will easily recommend everyone should buy 10-cent stock today, okay? Because no one thought about the multiple decision-making problem, right? And then everyone recommends buy 10 cents stock, everyone buys 10 cents, the stock price goes up artificially. You destabilize the market. And of course, the Chinese government is totally aware of this, and so they clamp down on this, rightly so. Rightly so. Okay, so the alternative is really not that mysterious. Create a market on the two sides of it. So like if I go to Shanghai, I get involved in a market between me and the other side. And it's all about data analysis. It's not just microeconomics. It's all about data analysis. And so are companies doing this? Well, not enough. It's surprising how few companies are thinking in this way. Okay, so as an academic, I work on these things. What are the underlying mathematical and algorithmic ideas that are needed to solve these kind of problems? They don't exist, so we have to work on them. So I'm going to give you a couple of examples before I run out of time, and give you a flavor of the kind of work that could be done. That is, I hope you see that I have real interest in company and business plans, and so every one of them has kind of a business plan behind it. And when I say business plan, I mean kind of startup business plans, things that you guys could do, or every one of us could do. So let me tell you about bandits that compete. So this is, to me, an attempt to combine the elementary principles of learning systems with the elementary principles of economic systems. And what is the elementary principles to me for learning systems? It's really a bandit. It's not supervised learning, and it's not reinforcement learning. It's a bandit. What is a bandit? A bandit has got K options, and it doesn't know which one of them is the best. It has to learn. No one's telling it. Okay? There's no supervised data. So it tries each one of them a few times, right? That sounds like reinforcement learning. Well, reinforcement learning doesn't tend to do it just does the exploit side, it does the optimize thing. The core part of the learning problem is to explore. All right, so I could try each one of the arms a few times and maybe discover that arm one is looking pretty good. But if I now lock into arm one forever, there could have been another arm which is better, and I'm going to feel a regret forever, a huge regret. Over time, it'll accumulate. And so I don't do that. I don't lock in. But how do I not lock in? Do I just randomly choose another arm from time to time? That's called epsilon greedy. It's a terrible algorithm. It doesn't work. Okay, there are better algorithms. All right, so anyway, there's a whole rich set of problems there. All right, but now let's not just have one person playing a bandit game. They have K arms, but it does have two people playing the game. And if both of them pick arm one, only one of them gets it. Okay, that's a little bit like the restaurant problem. If both of us want to go to a restaurant, there's a limitation on the number of people who can go to the restaurant. All of us can't do it. All right, so how do we do this? So first of all, my students, Lydia Liu and Jorge Mania, are working with me on this. So here's kind of the setup of multi-arm bandits. You know, a person, entity, decision maker of some kind is choosing between a bunch of options. They choose one, back comes a reinforcement signal. They choose another one, comes back a reinforcement signal. So there's a unknown preference that they have, and they start to learn about that. So that's the learning problem. What's the economic problem? Well, the economic problem is what's called a matching market in our little model here. So you all know what a matching market is. It's like interns in hospitals, people looking for jobs. What job do people get? You can't put everyone in the same hospital. So some doctors go to one hospital, others go to another hospital. Everyone has their preferences, and they give these preferences to an algorithm, and the algorithm uses those preferences to find the best matching. That's called the Gale-Shapley algorithm. It's widely used in real life. Okay. All right. Now, that microeconomic problem is set up and solved, where you assume you know the preferences. Everyone knows their preference, and they can give them, they can explain them to a central decision maker. Of course, that's not the real world in many situations. We don't know our own preferences, and we certainly can't explain them. So how do we put these two ideas together? What if the participants do not know their own preferences because they have to have some experience in the world before they know that, okay, with repeated interactions? And then how do they explore and exploit when they're not the only person doing the optimization? What if they're doing it in the context of other decision makers? What are the mathematical principles there? Okay, so we have these competing agents. All right, now there are multi-agent systems and multi-agent RL and all that, but I find it hard to read that literature because I don't see principles. I just see people building systems and trying them out. So what are the underlying principles? What's the regret bound? What's the algorithm that achieves it? Okay, so let's set up a bandit market. On one side, you've got agents who get noisy rewards. On the other side, you have arms that have preferences back on the human. So if you and me both pill arm one actually, unbeknownst to us, has a preference between the two of us. And it may be random, but the arm one has it. And so arm one's gonna pick you instead of me, all right, for some, and I start to see that. I say, well, I really like arm one because I get a lot of reward there. But she's also picking arm one, and she seems to get it more often than me. So I better start to pick arm two and K to explore a little further than I otherwise would have done. I'm hedging my bets. It feels like real life. I gotta hedge my bets and explore more. All right, so I will have a bigger regret, but how much? Is it gonna be terrible? All right, is there an algorithm that will achieve good regret for all of us? Is it incentive compatible? All right, so here's the regret we defined, and I'm not gonna get into the math here, but it's just, regret is a notion of how good you would do in hindsight. If at the end of the day, you had all the information you needed and you set up the optimal decision-making system, how well did you do relative to that? That's what regret is. All right, so we have a new measure of regret here, which is regret relative to what the Gale-Shapley algorithm would do if it knew all the preferences. And that's our baseline. All right, so how does our regret go relative to that? Is it growing linearly where we're not learning anything, or is it growing, say, logarithmically? That would be fantastic, or maybe square root. Okay, so here's an algorithm we've analyzed. We call it Gale-Shapley upper confidence bound. Okay, so upper confidence bound means if I have these K arms, I don't just take the mean of each one of them and see which is best and go with that. All right, I put a confidence interval on each one of the arms based on the data I've gotten so far. Okay, this is something, again, we're not doing very much in the neural network world. We don't have any confidence intervals. We just assume we have so much data we don't need them, which is ridiculous. But anyway, each of these arms has a confidence interval, and what we do is we pick the upper confidence bound. Now, an upper confidence bound can be large because the whole distribution is really high. Okay, and so therefore the confidence bound will be large, and so I should pick that arm. That's exploit. Or it could be high because I have very big uncertainty about that arm. I haven't explored it enough. So I should pick it because I want to explore. And if I start to pull that arm, I'm going to realize, oops, it's bad, the confidence interval will shrink, and I will not pick it anymore. All right, so upper confidence bound is a really amazing idea. It combines explore and exploit in one idea. All right, so our algorithm is pretty simple. We keep upper confidence bounds for each agent, for each arm, and then they report back their upper confidence bound, and then you run Gale-Shapley on that, okay, not on preferences. All right, and we prove theorem that says that there is a regret, and the regret is actually logarithmic. So that's the best you can do, okay? So this algorithm really, really works. There is a term, which is called delta squared. If it's big, that's good. If it's small, it's not. It is a function of the other agents. So it's this kind of thing I was talking about. If she's pulling arm one and I start to see that, I'm going to have to explore the others more, and I will pay for that as regret, so we can quantify that. Okay. I think I have 5 minutes. Is that right? Where's Bill? Okay. I'm going to go for 5 more minutes, I think. Okay, so here's another class of problems which have to do with our gradient-based machinery. That's what we're really good at in this era, taking gradients of things and doing it at scale and getting systems to learn from gradients. All right, well, what if the systems are strategic and they have to learn in the context of other decision makers? Well, we have to have equilibrium now. And so the classical equilibrium is a Nash equilibrium where multi-players, each one of them is as happy as they're going to get in the context of the other players. Right? Well, can we find Nash equilibrium? This has not been a problem that's been that much studied in economics, really. There's certainly some work, but not that much. What about in our modern world with all these gradient-based algorithms? If one agent's doing a gradient descent and another agent is doing gradient ascent, because they're competing, what happens with that algorithm? That has been studied, and it's known it doesn't work. Interesting. Gradient descent doesn't entirely work. So with Eric, we've been looking into these problems. Okay, so here's just a little quick setup. A zero-sum game has a function f that is being minimized by one agent and maximized by the other agent. You can talk about the gradient, and you can talk about the Jacobian matrix of the game. Simultaneous gradient descent has two main issues. In fact, it doesn't go down to the answer in one direction and up in the other direction. It can go into limit cycles, which are bad. There's no answer coming out. Also, a Nash equilibrium is an equilibrium which is axis parallel. It's a saddle point in the space of the f function. So one agent wants to go down, so it looks like this for that agent. The other agent wants to go up, it looks like this for that agent. That's a saddle point. But it's a saddle point that's axis parallel because for one agent you want to go down, the other one you go up. If you just throw down some Nash equilibria in a high dimensional space, you will also almost certainly create some other saddle points that are tilted saddle points, just topologically. Those tilted points, from the point of view of a gradient algorithm, look perfectly good. They will go down and up to that just as well as they will to the axis parallel. But those are not Nash equilibria. Those are bad solutions where neither person is happy. But unfortunately, our algorithms will get just as sucked into them as they will the other. So people, when you run these kind of algorithms, they can get rid of the limit cycles with some extra work, but they start getting these bad solutions a lot, right? And if you've been following neural network literature, you know about GANs. That's kind of the hot topic at the moment. Those are based on a game theoretic Nash equilibrium formulation, and they sometimes get bad answers, and this is part of the problem, okay? All right, so can we do some mathematics? Can figure out how do we avoid this? So here's an example of just running some of the existing fixes to this problem: gradient play, symplectic gradient adjustment, and so on. The green crosses there on the left are Nash equilibria. And all these algorithms are converging to those nicely, very nicely, no limit cycles. The blue thing in the middle is a tilted saddle point. So these algorithms are all going to that, okay? Which is not a Nash equilibrium, so it's not game theoretically good to be there, but they go to that. All right, so we've defined the new algorithm, and I'm not gonna get into details, but it's up on the archive if you want to see it. It is called local symplectic surgery. It cancels the symplectic component of the gradient field. Okay, all these gradient algorithms have a gradient flow. Those flows have multiple components, and some of those components are good, some of them are bad. Symplectic component is good for accelerated algorithms like Nesterov. It's bad for this. This is what we've discovered here. And so if we cancel it, we get rid of the limit cycles. That's great, but also we do not go to the non-Nash equilibria. All right, so here the algorithm you can see there, the blue thing in the middle. The red curve is our algorithm. It heads towards it, but it sniffs it out and realizes it's not good, and it heads away from it and goes to a Nash equilibrium. Okay, so a little simple algorithm up there on the upper left will do that. All right, so we've applied it to some of the neural network learning, GAN things. This is on the top row is this algorithm LSS. The ground truth is over on the right with the, this is a mixture model with the little red dots. And you can see all the algorithms below that are having troubles. They're getting this so-called mode collapse problem happening. Whereas the LSS is the best of the bunch. So we've done a whole bunch of other experiments like that. Okay, Bill is now arrived. Bill, do I have 2 more minutes or am I done?
I think you have 3 more minutes.
3 more minutes? Okay. All right, so let me just briefly say this other project with Chi-Jen and Praneeth Netropali. We're trying to understand more deeply the mathematical theory of non-convex, non-concave optimization. So we're trying to do game theory now where it's non-convex, non-concave. So we're using all of our things we've learned about non-convex optimization and trying to play it to non-convex, non-concave game theory. Okay? And let me just tell you without getting into even the slides, let me just say what's happening here. So we have a new notion of what it means to be locally optimal in these problems, right? And we show that Nash equilibria are not the right kind of equilibrium to be studying here. There's another kind of equilibrium called a Stackelberg equilibrium. It's more of a sequential equilibrium. And it's more appropriate when you have an adversary. Okay, I'm going to make a decision. The adversary will look at that. They'll do something bad to me. And I want to think ahead through that sequence of steps. That's a Stackelberg equilibrium. Long story short, if you set up non-convex, non-concave Stackelberg equilibrium, then actually stochastic gradient descent converges to those equilibria. And it's if and only if. Okay? So it's a characterization of stochastic dynamics in game theory. Stochastic gradient is actually well set up for Stackelberg equilibrium. So it's a different kind of equilibrium we study. Okay, so I'm going to finish there. Let me just return to my opening themes. I'm a mathematician, engineer type person. I just like to get it down to work on hard problems and sort of see where they'll go, and then I want to tie them to business models. Okay, so I've tried to do a little bit of all the above in the talk. I don't think we've solved our mathematical problems, but that's not an issue, that's a challenge. That's great. We have decades of work to do here, right? And I personally feel that we should not get distracted by this artificial intelligence talk about replacing humans and copying our intelligence. We don't know what that means, and I think selling that is what we're seeing in this era. I think it's irresponsible. What we do have is data and humans critically involved in the use of that data. And we've got to think about the overall system that includes the humans and the data and the consequences of all this. And so that is, I think, an interesting new field emerging that bridges industry and academics in a way never seen before, I think. I think the chemical engineering era was fantastic. There was industry and academics that created this new thing called chemical factories. They changed our world. We're seeing an emergence right now, a similar kind of nexus of things. But we just got to sober down our language and just talk about the challenges involved. Thank you very much.